Hi, I am Sarthak, and this is a demo video for Lab 1 for EE533 under Professor Young Cho. The part 1 of the lab expected us to compile the code and run it as it is, as provided by the professor, to understand the communication between a server and a client. I had to make a few modifications to the code before compiling to get it to run, uh, such as I had to add a few of my own printf statements to make sure that every single part of the code was working correctly. I had to make the argument of this error function constant and add a few libraries for the compilation. So I'm going to show you exactly how this works. So currently we are going to be using the TCP/IP protocol, not the Unix tree, which we'll be doing later. So let's say I invoke the server with the port 51,000. Now the printf statement suggests that the server is actually listening for a connection, and as soon as my client starts building that connection, we're going to see how it works. Uh, let's say I have /client here on my client machine, then the IP address, and then the port. So this IP address 192.168.100.4 is the IP address of the server I'm trying to connect to. How I got this IP address, I'll show you in a second. Now we're going to have to enter the message, but before that we see that the moment we ran the executable for the client code, the server says connection accepted. Okay, let's type a message for the server from the client, and immediately we see that the message was transferred onto the server. Then the server sends an acknowledgement back to the client, completing the TCP/IP communication. All right, so I'm going to show you how I got this IP address. For that, I just went to my server, typed in ifconfig, and saw this inet here. 192.168.100.4 is the IP address of my server currently. The next part of the lab was to figure out how to modify the code for the server to accept connections from multiple clients. Currently, as soon as one of the clients connected, send a message, the connection died down. We need to have the server listening for multiple connections and not die down. For that, we had to make a few modifications to the original code, like so. On the left hand side, we see that we had to add this while loop, which is essentially an infinite loop that would keep running and running and running and look for more and more clients without killing off the connection. Uh, this fork here basically spawns off multiple children and parent processes, stores their process ID into the PID variable, and then calls the do stuff function. The do stuff function basically is written to read to different clients and write from different clients or write to different clients. Now to demonstrate, I'll again start off my server. Again, it is listening on port 51,000, waiting for a connection from the client. Let's say right. Let's say this is client 1, and we see that the server is actually looking for other connections as well after it has gotten a message from my client. Now I have opened a second terminal to simulate a second client. So let's say I write the same command for client number 2. Again, as soon as it receives the message from client number 2, it sends an acknowledgement back and waits for other clients. And again, let's say I'm running a few more times just to get the point across. Now I will see that this code actually works perfectly fine. Unfortunately, one of the problems with this code is that apart from spawning of multiple children and parent processes, it also spawns of multiple processes, which takes up a lot of memory. Now, how do we figure that is we go to the terminal for the server, type in psaux, which is basically to figure out all the processes that are running, pipe grep defunct. Now this will give me all the processes that are currently running for this particular port. And as we see that there are multiple processes running for the same server. We do not want that. In case there are hundreds of clients, this is actually going to take up a lot of memory and will cause problems. How do we solve this problem? To solve this problem, I just had to make a very small change in the code where, let me show you. The only change I made in the multi-signal code, multi-client code, and this killing the zombie code is addition of this statement called signal. I had to add a library called signal.h, and essentially what this signal port, the signal statement will do is kill off any random processes that have spawned off due to multiple clients. To demonstrate, let me run this particular code. All right. Let's run to multiple clients again. Let's see how it actually works. Client 2, then let's say client 3. This will be client 4. This will be client 5. All right, so now that we have a few clients running or simulated, we'll go and see if that actually solved the problem. Now, as we see that in the previous multi-client code, we had multiple processes running across, but here we just have the single one. This is always going to appear in the psaux because this is the psaux process. This is not defunct, unnecessary zombie process. So as we see that addition of that one single line actually helped us quite a lot, removed all the waste, I mean, not waste, but unnecessary processes and saved a lot of memory for us. The next part of the lab was actually to play around with a few different sockets. So we use the UDP socket. Currently, whatever examples I've shown are TCP IP sockets, stream sockets, in which the server gets a message from the client, sends an acknowledgement back to the client to tell it that the message was received. If there's a drop somewhere, the client would know and actually would resend the packet. Unfortunately, in UDP, we do not have such a mechanism. UDP has no way to know whether the client that sent a packet was dropped or not. The server does not send an acknowledgement back. Neither does the client understand which packet was dropped or if the packet was dropped. Now that increases the bandwidth and the throughput quite a lot, but the disadvantages are also plain to see. So UDP essentially is utilized for communications that are very short or ephemeral in nature. And essentially the changes to the code are as follows. Most of the code remained the same, apart from the fact that the socket that we use is now using sock underscore dgram instead of the previous one where we utilized sock underscore stream. So this dgram basically represents the UDP socket. Apart from that, there are other two functions which we are not going to use. One is read and one is write. We were using read and write functions for multi-client and TCP-based servers. As you see on line number 97, we see the read here, then we see the write here. But for UDP, we are going to use different functions called receive from and send to. Again, this is an infinite loop which keeps listening for multiple connections and receiving message from it and sending message to it to acknowledge connection. Similarly, for the client side of things, we are again going to use the send to and the receive from functions instead of the read and write. The rest of the code remains same largely. All right, to demonstrate, let me run this UDP executable. Now, the moment we press enter, we see that instead of waiting for the client to actually start a connection, the server is actually listening for a connection almost immediately and will accept whatever connection comes through. It does not have to wait for anything for the client to actually send a request, right? And the same thing here, we are going to use client underscore UDP. Unfortunately, we are not going to see any difference here because essentially this is a very small communication server, right? But if the number of clients were large or the number of messages that we were sending was quite large, we might actually see packets dropping. Again, same thing here. Essentially, we don't see any difference from the multi-client apart from the changes in the code that I mentioned earlier. Okay, finally, we were supposed to be using a Unix domain where we are supposed to be giving a file path instead of the IP address that we were currently giving from the client. So for Unix servers, we actually require that the file exists or some file from our own server. Now, in order to do that, I'll show you exactly how. All right, so let's say I was to send this file or receive this file. So it's waiting for the client to actually send this file to us. In this case, we'll give it the same file. And again, as we see on the other tab, we'll see that this connection was established. We send the message, which was again the acknowledgement of which was received back to the client side, and we see that in the file path actually works instead of giving an IP address like we were giving earlier. So this was my attempt at a demo for Lab 1. Thank you very much and have a good day.